Welcome to today's paper reading. Today's paper is titled Conversational Prompt Engineering. This paper was published on the AR14 preprint by Liat, Ein-Dor, and colleagues from IBM Research. The abstract highlights the challenges associated with prompt engineering, which is often tedious and time-consuming, requiring significant expertise and thus limiting its widespread use. To address these issues, the authors propose Conversational Prompt Engineering, CP, a user-friendly tool designed to help users create personalized prompts for their specific tasks. CP leverages a chat model to interact briefly with users, assisting them in articulating their output preferences and integrating these into the prompt. The process of CP involves two main stages. Initially, the model uses user-provided unlabeled data to generate data-driven questions and shapes the initial instruction based on user responses. Subsequently, the model shares the outputs generated by the instruction and refines both the instruction and the outputs based on user feedback. The final result is a few-shot prompt, where the outputs approved by the user serve as few-shot examples. A user study on summarization tasks demonstrates the effectiveness of CP in creating personalized, high-performing prompts, suggesting that the zero-shot prompt obtained is comparable to its much longer few-shot counterpart, indicating significant savings in scenarios involving repetitive tasks with large text volumes. Large language models, LLMs, are widely used in various enterprise applications, such as automating customer support, retrieval-augmented generation, RAG, and text summarization. However, crafting effective prompts for these models is challenging. Prompt engineering, P, is computationally demanding and time-consuming, requiring a deep understanding of how LLMs interpret instructions. To address these challenges, Conversational Prompt Engineering, CP, is introduced. CP eliminates the need for labeled data and initial prompts by using chat models to assist users in creating prompts through a user-friendly conversation. This approach is designed to help users clearly define their tasks and expectations, making it easier to communicate their needs to the LLM. In the realm of large language models, LLMs, the quality of prompts plays a crucial role in performance. One notable strategy is chain-of-thought prompting, introduced by Wei et al. In 2022. This method involves adding reasoning steps to in-context examples to enhance performance on complex tasks. Another significant area of research is automatic prompt improvement. For instance, Shin et al. 2020 use trigger tokens to optimize prompts and masked language models. Additionally, Zhou et al. 2022 and Yan et al. 2023 developed an iterative process where an LLM generates prompts, which are then evaluated and refined. Yi et al. 2023 proposed a meta-prompt to guide the LLM during the prompt enhancement process. Human-in-the-loop mechanisms also play a vital role. Kim et al. 2024 introduced EvalLM, an interactive system designed to iteratively refine prompts based on user-defined criteria, improving both the prompts and the evaluation criteria used to assess them. The CP system operates through several key stages. Initially, the user selects the target model and uploads unlabeled data. CP then engages in a discussion with the user to create an initial instruction based on the user's data and preferences. This instruction is refined iteratively based on user feedback. The refined instruction is used to construct a prompt, which is fed to the target model to generate outputs. The user provides feedback on these outputs, and CP refines them until they meet the user's approval. The final stage involves the convergence on a CPFS prompt, which is shared with the user. The system also includes a web interface with modules for chat, survey, and evaluation, and features context management and chain of thought, COT, for more careful model guidance. Figure 1 illustrates the Conversational Prompt Engineering (CP) workflow from the user's perspective. The workflow consists of several key stages: initialization, initial discussion and first instruction creation, instruction refinement, output generation, user feedback and output enhancement, and convergence on the CP few-shot (FS) prompt. Each stage can involve multiple turns of conversation between the user and CP. The goal is to iteratively refine the instruction and outputs until the user approves them, resulting in a prompt that aligns with the user's requirements. Figure 2 illustrates the sequence of messages exchanged among the user, system, and model during a chat session with CP. The process begins with the user approving a suggested prompt and continues through the approval of the output for the first example. System messages are abbreviated for clarity, with full details available in Appendix B. The figure uses suggested_prompt, example_I, and prompt_output_I to represent the prompt proposed by CP, the ith example, and its corresponding output. Notably, messages below the dotted line are sent with a context that has been filtered to exclude irrelevant information, enhancing the focus and efficiency of the interaction. In the design and implementation of the three-party chat, the interaction involves three key actors: the user, the model, and the system. The user communicates with the system through a user interface. The model, which is a large language model, LLM, handles core capabilities such as user data analysis, instruction refinement, and output enhancement. The LLM is designed to respond in a specific API call format, and each response triggers an action by the system. The system orchestrates these interactions, dynamically invoking multiple system instructions throughout the chat, which is a departure from typical single instruction models. This dynamic approach allows for greater flexibility in managing the chat. The implementation specifically uses Llama 3-70B as the LLM. The system also manages context-free side chats and analyzes user feedback using chain of thought (COT) techniques to potentially modify instructions as needed. The user study involved 12 participants who engaged in summarization tasks with CP. Participants were encouraged to have open-ended conversations with CP to develop prompts. Following their interactions, they completed a survey rating their satisfaction with CP instructions, the benefits of joint conversations, the pleasantness of the chat, and the convergence time. The survey results indicate high satisfaction and benefits, with an average convergence time of 25 minutes. Evaluation results showed that participants preferred summaries generated by CP prompts over baseline prompts, with CP ZS and FS prompts being ranked best in 53% and 47% of instances, respectively. Table 1 presents the results of a user study conducted to assess the benefits of CP in practical scenarios, specifically in summarization tasks. The survey results indicate high levels of satisfaction with CP instruction, benefits from joint conversations, and pleasantness of the chat interactions. However, convergence time was rated slightly lower, averaging 25 minutes, suggesting potential areas for improvement in future work. Table 2 illustrates the process of refining an instruction during a chat with the CP system. The initial instruction was to generate a list of main claims for each debate, grouped by topic, in 1 to 2 concise sentences per claim. The final instruction, after refinement, specified avoiding specific examples and breaking down complex or multi-topic claims into simpler separate ones. The average distance between the initial and final instructions was 96.3 characters, indicating significant changes throughout the chat. Figure 3 displays the evaluation results of generated summaries, categorizing them into best, middle, and worst rankings based on user preferences. The data is aggregated from 12 chat sessions involving 112 examples. Notably, summaries generated by the CP prompts were favored over those from the baseline prompt. Specifically, the CP-ZS and CP-FS prompts were ranked best in 53% and 47% of instances, respectively, indicating a high level of user satisfaction with both prompts. This suggests that the CP effectively integrated user preferences, making few-shot examples unnecessary and potentially reducing costs for users performing repetitive tasks on large volumes of text. The authors introduced CP, a novel approach designed to assist users in the critical task of prompt engineering, P, especially for repetitive tasks across large datasets. The user study focused on the complex task of summarization, showing CP's effectiveness in generating efficient prompts that align with user expectations. An open question is whether these prompts can be further improved by using them as initial prompts for existing automatic P methods. Additionally, it would be intriguing to extend CP's application beyond prompt generation. Given the recent interest in large language model, LLM, empowered agent systems, exploring whether CP could assist in planning and creating agentic workflows would be valuable. Thank you for watching.